Assalamu alaikum warahmatullahi wabarakatuh and hi. In this video, we will look into Pelton turbine example. A Pelton wheel operates with a gross height of 530 meters and a flow rate of 9 meter cube per second. The penstock length is 800 meter. Its diameter is 1.2 meters and its RMS roughness is 0.1 millimeters. The minor losses increase the equivalent length of the penstock to 880 meters. The hydraulic efficiency is equal to 0.84 and the shaft speed is equal to 650 rpm. Find the effective heat and the power delivered by the turbine and the specific heat or the specific speed, and from it the recommended number of jets and the number of buckets in the wheel. The nozzle coefficient is equal to 0.97 and the ratio of the blade speed to the discharge velocity is equal to 0.45. Before we solve this question, first we have to um, uh, list down, or we have to find the some important values that given, or important information that are given in the question. Okay, first we have the gross head, which equal to 530 meters, the flow rate inside the penstocks 9 meter cube per second, and the length of the penstock 800 meters, and the diameter of the penstock is equal to 1.2 meters, and the RMS roughness of the penstock is equal to 0.1 millimeters. Okay, due to the RMS roughness inside the penstock, the equivalent length of the penstock now become 880 meters, and the hydraulic efficiency is equal to 0.84 and the shaft speed is equal to 650 rpm, or revolution per minute. And we also have the nozzle coefficient, which equal to 0.97, and the speed ratio, which equal to 0.45. In this question, speed ratio use lambda symbol here to represent speed ratio, but sometimes some textbooks also use ku, k subscript u, to represent speed ratio. Okay, now uh, before we can solve uh, the problem A, we have to find the velocity of water in the penstock. Okay, the velocity of water in the penstock can be calculated using the flow rate. Okay, by having flow rate and area of the penstock, we can get the velocity of water using this correlation. Okay, so velocity of water inside the penstock is equal to Q over A, which is the flow rate over the area of the penstock. Okay, the penstocks is usually, the area of the penstock is in circle, so circular area is equal to pi d squared over 4. So if we rearrange the area of circle equation inside this equation, we will get 4q over pi d squared, and we plug in the information that we can get from the question, which q equal to 9 and d equal to 1.2. We will get the velocity of water inside the penstock is equal to 7.96 meter per second. And here we want to calculate Reynolds number here because we want to get the friction factor inside the penstock. Okay, so Reynolds number, I believe the equation of Reynolds number, you have encountered this equation so many times in fluid mechanics classes. So if we look into Reynolds number equation here, we have rho, which is the density of water, and the Vp, the velocity in water inside the penstock. Dp is the diameter of the penstock, and mu here is the viscosity of water inside the penstock. So we have all this information for density and viscosity of water. um, you have to memorize this because this is the very common fluid in our daily life. Okay, so rho for water is equal to 998, and viscosity or mu for water is equal to 1.01 multiplied by 10 power of minus 3. We plug in all these values inside this equation. We will get Reynolds number is equal to 9.44 multiplied by 10 power of 6. Okay, now we want to use that Reynolds number value to calculate the friction factor inside the penstock using the Colebrook formula. The Colebrook formula, I believe you have encountered this as well in fluid mechanics lesson or classes. Okay, from the Colebrook formula, give the friction factor value of 0.0116. Okay, so why we want to get this friction factor value is because we want to calculate the head loss due to friction inside the penstock. So the head loss due to friction inside the penstock can be calculated using this equation. If we look inside this equation, we already have all the information that needed to calculate head loss due to friction. So we just plug in all those parameters. The F is the friction factor, L is the length of the penstock, Vp is the velocity of water inside the penstock, D is the diameter of the penstock, and G is gravity. So we will get the head loss due to friction inside the penstock is equal to 27.4 meters. Okay, next, the gross head is measured as the elevation difference between the headwater and the nozzle. Only the upstream losses are included in the calculation of the effective head, and whatever kinetic energy is left after the water is discharged from the wheel is taken into account in the turbine efficiency. Thus, the turbine efficiency is the total to static efficiency. Okay, now we can calculate the effective head, which equal to the elevation of water, or the which we can get from question, which equal to 530 meters, and the head loss due to friction, which we just calculated before this, equal to 27.4. So we get the effective head is equal to 502.6 meters. Now we want to calculate the power delivered by this turbine using this equation, the power equation. Okay, this again in this equation, eta is the efficiency of the turbine, rho is density of water, q is the flow rate, g is the gravity, and h subscript e is the effective head. All these parameter we have the values, and we just plug in all the values inside this equation, and we will get the power delivered by this turbine is equal to 37.20 megawatt. Okay, next we want to calculate the specific heat, the specific speed. Okay, the specific speed can be calculated using this equation. Okay, omega s is specific speed. Omega is the shaft speed. Q is the flow rate. H subscript E is the effective head. We just plug in all the values for these parameters, and we will get the specific speed is equal to 0.347. And um, we have here the table show the table here show the power specific speed ranges of hydraulic turbine. Okay, usually for Pelton wheel, Pelton wheel and French's turbine. Because now we are looking into Pelton wheel. Okay, we want to get the recommended number of jet. Okay, so we have the specific speed calculated here is 0.37347, which is somewhere between 0.12 to 0.36 here. Okay, so the recommended number of jet is equal to 4. Okay, so that's why we want to calculate the specific speed to get the recommended number of jet. uh, yeah, we know the recommended number of jet is 4, hence the discharge from each jet is Qj equal to 2.25 meter cube per second, which is we just divide the flow rate 9 meter cube per second by 4. We will get Q jet equal to 2.25 meter cube per second. And we can get the discharge velocity V2 using this equation. V2 equal the nozzle efficiency to square root of 2GHE. So all these parameters, we have the values, plug in the values, we will get V2, or the discharge velocity, is equal to 96.3232 meter per second. Okay, so the nozzle diameter now can be determined using this equation. D equals square root of 4qj. Qj is the jet flow rate over pi V2. So we have Qj and we have V2, so we can calculate the nozzle diameter, which equal to 0.173 meters. And the blade speed, we have looked into this equation before in class. So the blade speed U is equal the speed ratio multiplied by V2, or discharge velocity. So we have speed ratio equals 0.45, and we just calculated speed velocity up there. We plug in the value inside here, and we will get the blade speed is equal to 43.35 meter per second. And therefore the diameter of the wheel, the equation is D equal to U over omega, or the shaft rotation. So we have shaft rotation value in question, and we have calculated U here. Plug in the value inside this equation, we will get the diameter of the wheel, or of the Pelton wheel, is 1.27 meters. And finally, we want to calculate the number of bucket. Okay, the number of bucket can be calculated using this formulation. Z, capital Z, equal diameter of the wheel over 2 diameter of the jet. Okay, so we have D value here, plug in inside here, and small d here, plug in here. We will get Z, capital Z, equal to 18.7, which is Z, we can say Z, or the number of buckets recommended for this particular Pelton turbine is equal to 19. So hopefully now you know how to solve a Pelton turbine question problem, and see you in next video. Bye bye. Thank you.